Yeah, I will be the chairman. So we start with Peter Ring, but I don't have to introduce, who will talk about relativistic Brueckner-Hartree-Fock theory. Please, Peter.
Yeah, ladies and gentlemen, I would like to thank the organizers very much for having invited me here. And is it working now? Yeah? Okay. Should I? Okay, then. So is it working? Yeah, it's working. So I'd like to talk today about relativistic Brueckner-Hartree-Fock theory. No. So relativistic Brueckner-Hartree-Fock theory. Now, my problem is certainly I'm working at that, right? So I wanted to tell you something new. I was working on pygmy resonances many years ago, but so I made a connection. This is, so to say, the idea to make an ab-initio approach to these density functional theories, and everybody needs density functionals for doing RPA calculation. So it's part of this is a project, part of this is using. So let me start with first with. This doesn't work. It was working before. I must use it here. It was working before. Yeah, but not the next slide. Probably this here. Yeah, so I must make a mixture here. Okay, so first I'd like to start in memorizing to my good friend and collaborator Peter Schuck. He has died in the last months and we are all very sad about it. I must say that I owe a lot to him. He invited me in 72 or 73 to work on this book, and this was a big success for both of us. This is a very sad story for many of you, and most of you probably know it. I only want to mention that we have written together with Gerd Röpke, who was a collaborator of him in the last years. We wrote an obiter in this journal of the NUPEC, which is coming out in December. But we also plan to produce an issue in a special issue for people who want to contribute to that issue. So they should get in contact with me. It will appear in European Physical Journal A in a very similar way as the Milano group has it done 2 years ago for Bortignon. And so I invite you to participate there. So let me start now with my talk. I have, first of all, I will give some motivation. Then I will talk about relativistic Brueckner-Hartree-Fock theory, applications to finite systems, and then the full solution for nuclear matter. Now, the idea is to go to ab-initio calculation. There are ab-initio calculations for light nuclei, and there you can do a solution by configuration mixing. Or so ab-initio is possible, but the results which you have here are usually very complicated. So for heavy nuclei, you need density functional theory. And this is for simple description, easy to visualize, but at the moment it's phenomenological. So the idea to make an ab-initio for density function theory. And this is the goal of the whole thing, but at the beginning, at the moment, we are still very much at the beginning. Now, let me talk about why density functional theory is important for these low-lying modes, which we are talking in this conference. This is a work which was done in the 90s. You take density functional theory and you determine then time-dependent density functional theory. So you start with a solution of a static solution, and you constrain it a little bit, so you push it a little bit further out, and then you start, it's no longer a static solution, and you solve the time-dependent mean field equation, and then you observe oscillations. And if you make a Fourier analysis, you basically get a resonance here. And now you see we have done it for different parameter sets, NL1, NL3, NLSH, NL2, and you get different things here. But this means just these different parameter sets have different compressibilities. So this was basically the first game. And the next thing was, this was done at a time when people did relativistic RPA calculations in Orsay and got nonsense. They just have not done it properly. We have realized one has to treat in relativistic RPA also the negative energy states probably. If you include that, then you can do it. And nowadays we did it, but at the beginning, this was just a time-dependent calculation. Now, let me show you. Then we did many more calculations. For instance, the iso vector dipole resonance. And you see we get very nice agreement with the experiment for the peaks, certainly not for the width. And this was the isovector dipole, but also for the monopole. This is the thin regions. And we got excellent agreement just with this parameter set DDME2. There was no adjusting anything there. At that time, Squirm people could not reproduce at the same time thin and the lead region. So I don't know if this problem in the Scrum community is solved by now, but at that time we could do it. I don't know why. I always thought maybe it has to do with that we took a very good particle-particle, we took Gonier pairing, which is probably much better than this finite zero range pairing in the Gonier case. Now we get also others for the isoscalar quadrupole resonance. You see, there are not so many experiments, but we get relatively good agreement. And then we come now to these low-lying modes. Actually, this is a calculation just before the experiment was done. This was actually Niels Parr, was his PhD work, who is here. He did that, and he found that there is a low-lying mode in lead 208 at 7.29 MeV. And we published that, and we wrote in the paper, this should be measured. And then this is a paper now of this group who has measured that. And this was certainly many people in the audience, Horst Lenske, Achim Richter, and von Neumann-Kosel. And they cited us that they should measure it. You see it here, and they measured it. So the theory was first. Now here, you see the big dipole resonance. We have seen it also this morning for this thin 130, and this is this inclusion of this particle vibrational coupling. And this has been done by Elena. And we also see here the different contribution of these different states. We have seen several of those measurements already, calculations already this morning. Now, Ab-initio deviation of density functional theory. Now, in principle, in density functional theories, there is not so much done so far Ab-initio. The natural thing, to my opinion, is go back to Brueckner, because Brueckner was done in the 50s as an Ab-initio theory before density functional theory was known. Brueckner had only the disadvantage, it didn't work. So non-relativistic Brueckner didn't work. The idea was you start with the mean field concept, but you use an effective density dependent interaction. And this is later on it doesn't work, but Wotherer realized that if he doesn't do that, but if he includes, if he does a phenomenological density dependence, it works well. In that time, in the non-relativistic case, this did not work. And the reason was there were no three-body forces. So this took until the end of the 70s, people realized it doesn't work. And then in 1980, people used relativistic Brueckner. And they found already in this time in 1980 that this works. One does not need three body forces. But there was a problem for now 40 years. There was no exact solution of the relativistic Brueckner-Hartree-Fock in nuclear matter. But there were so many different approximations which contradicted in some way. And There was also no solution of relativistic Hartree-Fock in finite nuclei. So that was the beginning when we started all that. And let me talk about those who don't know about Brueckner. I have grown up with Brueckner in the 60s, but nowadays people are not so familiar with Brueckner anymore. So Brueckner is basically had the idea that once the nucleons in the interior of the nuclear medium do not feel the bare force as the nucleons in free space. And this idea was in free space, you have free scattering, but that means you after the scattering process, you have all the momenta open, they can all be used. But in the medium, there are the momenta below the Fermi surface are occupied. So you cannot scatter into below the Fermi surface. And this reduces the strength of the force, and you get an effective interaction, which is called G matrix. And it is definitely density dependent because it depends on the Fermi surface. The Pauli principle forbids to scattering into states which are already occupied in the medium. And therefore, it depends on the density, and the force is then much weaker than the bare force. This means also nucleons move nearly free in the nuclear medium and feel only a strong attraction at the surface. So this is the basis of the shell model, which this was the idea of Brueckner. Now, let me talk it technically. You have here the free scattering equation, which calculates the T matrix, and from the T matrix you calculate the cross section. So this is basically you get experimental results. Compare with experimental results, and if you have these experimental results, you can adjust the force, the bare force. That's how the bare force is determined by those scattering. But this is the free scattering equations, the Lippmann-Schwinger equation. So here you have all the free momenta possible. In Brueckner, you cannot allow here, and this is called the Bethe-Goldstone equation, but it's a very similar equation to this scattering equation. And now you do it in a self-consistent way. You start with Hartree-Fock. In Hartree-Fock, usually you have some force. Let's say if the bare force is much too strong, it cannot work. The idea of Brueckner-Hartree-Fock is you use here the G matrix, which is much softer. That means you add here all these ladders here, you sum up all the ladders. So you have a double consistency. You must first solve this G matrix, and then you must again solve Hartree-Fock. So this is Brueckner-Hartree-Fock. And now, formally, you can solve this equation very easily. So you have here the G matrix, and this is a big matrix, and you can invert them. So basically, what you have to do, you have to invert a huge matrix, and you take into account here this Pauli operator and all these things. Now, here, these matrix elements, take all these matrix elements into account where you scatter a particle from below the Fermis above the Fermis. Now the point is the interaction is so strong that means you have a coupling up to very high angular momenta here. You have to couple it up to 1.3 GeV to get convergence. So this matrix here, which you have to invert, is huge. And that's our technical problem. We were able to do it for 016, but there we needed for this matrix the full space of the best computers available. All these supercomputers don't have a large memory, that's we also found. So we had in the order of 100 GeV, 100 giga-electron bytes, megabytes, and therefore we could not go further. So the problem is when we did it, we were able to do it for 016. Yeah, we used the relativistic bare interaction, that is the interaction of Brockmann and Machleit. So this is a bond potential, which is rather successful. And you see these are the parameters. It contains a number of meson and parameters, and this is all given by Machleit. And then if you use this interaction for nuclear matter, this is what first comes out. If you do a nuclear matter calculation, you come here, there are different versions of these calculations, But usually in the non-relativistic case, there is this well-known cluster line. You miss the experimental scattering area. But if you do it relativistically, you get that. So this was known in 1980, and therefore people should have done a relativistic calculation. Now, why is this working? Why do you need in the non-relativistic case 3 body forces and not in the relativistic case? The idea is, this was already put forward by Anastasio in 1981, that if you have the full propagator, then you can expand that in perturbation theory, and you see there are some diagrams where you have in the intermediate states, you have an antiparticle pair, and this basically is an effective 3 body force. So relativity introduces an effective 3 body force, and therefore you don't need it. Actually, this has been investigated more carefully by the Catania group. So they did a microscopic interpretation of their 3 body forces. So they used all kinds of diagrams with all kinds of approximations or not, but they certainly took also this diagram into account. And then they found out that this diagram makes the largest part of their phenomenological 3 body detection. So the understanding is, we don't need 3 body forces, at least not in the first place. Maybe if you are very precise, you need them still, but at the moment, we would not need them. This is the basic idea. So this is also seen here. This is a calculation for nuclear matter again. Here you have basically bond potential and this. When you do this Dirac Brueckner-Hartree-Fock, then you get very nicely this saturation properties. If you do it with 3 body forces, a non-relativistic N3LO, then you get it also nicely. But if you do it with normal Brueckner, you don't get it, and without 3 body forces. And so this is very clear that the 3 body forces replace that basically. Now, usually people did, if you go to finite nuclei, they make the local density approximation. That means they solve the Brueckner-Hartree-Fock equations at various densities, and then they map this density-dependent results on a Waleczka model, basically. And this yields then coupling constants, which depends on the density. And this is a Waleczka model. Now, that means this is a mapping, but this mapping is not unique. And many people have tried very different things, and the results are also very different. Here you see the results, what they get. So here is the O16 radius against binding energy. Here is the experimental value. This is just non-relativistic Brueckner-Hartree-Fock. This is a kind of approximation. There are many approximations. This is local density approximation. And there are so many in the last 20 or 30 years, there were so many calculated, but they scatter all over. Now, if you do now the relativistic Hartree-Fock, you have no parameter, you get here. So you're not there, but you get immediately much better. Certainly, you can discuss now why we are not there. There might be several reasons, but I'll come to that. Here you see, in order to get convergence, you have to go out up to 1.3 GeV, and then you have convergence of the solutions. But you need also these very big matrices, and basically we cannot go much beyond O16. So this is not what we want. Here is a little bit how you do it technically, but let me go on that. Here you see the results. Here results for the O16 energy, radius, matter radius, and the spin-orbit splitting. This is also an interesting point. Most of the Ab-initio calculation, if you look through the literature, they avoid to calculate spin-orbit. Very few give them, and then it's usually very bad. So this is a point which should be better in relativistic theory. Now, what do we get here? First of all, we have here, these are phenomenological RMF models, yeah, PKO1 with Hartree-Fock models. And you see, this is basically fitted. One should say they fit their parameters in order to get the binding energy and the radius. So these first two rows are basically fitted. Then this is our calculation with bond A. And so we are not fully at the experiment. We have some underbinding and the radius are a little bit smaller. And there are many other non-relativistic calculations, Brueckner-Hartree-Fock with AV18 or coupled cluster with NL3O or in medium SRG with NL3O, and then no-core shell models, self-consistent Green's functions, and many, many methods. And you see they are all very different results here. We also see here we show the spin orbit, and this experimental is 0.63, and we get 5.3. So we are still can improve, but it's still much better than this non-relativistic calculation. In all these others, which they don't even give it. Okay, so CSC, this is the spectrum, but this is basically not much new. We have also done one calculation for calcium, 40 and 48, and the results are similar. The quality, I only should say, we need for that a storage of 800 gigabytes, and we need a CPU time of 204 days. So this is really the end of our calculations. So now we want to go, this was finite nuclei. So the problem is basically we want to do it in, we first want to reduce the strain force. So we want to calculate a relativistic VLOK. And in order to do that, we need a relativistic version of Brueckner-Hartree-Fock or relativistic Hartree-Fock. And I just show you what comes in here. We have the single particle operator, the Dirac operator with the self energy here. And it has a sigma, a scalar and a vector part. You know that from the Waleczka model. But the self energy is determined by the Green's, by this G matrix and the density. And this contains now different terms, those which connect positive energy solution and those which mix with, or those which here. So basically what people did, they calculate only this part. Now, how do you calculate it? You solve the Brueckner-Hartree-Fock equation. And usually this is now a big problem. In principle, you should solve the Bethe-Salpeter equation. But nobody does that. So one must have a three-dimensional reduction of the Bethe-Salpeter equation. And there are several of those, and there are many discussions. But we use, and this is in this field usually done, we use the Thomson equation. And this is based on the Thomson equation. This was also used for the scattering process, because when they did the scattering and they adjusted this force, then they had to do it with the same equation. And what they did for adjusting the force, you need only positive energy solutions, because you have proton, 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 neutron scattering. So the scattering is basically that you mix only positive energy solutions here. In principle, you should also include those things for the Bethe-Goldstone equation. You have that, and you should have also others. But the people did not use it. They used only this part for the positive energy solution. I don't know really why, but I suppose this is a complicated code which has been developed in the early 60s, relativistic scattering, but only for positive energy solutions. So they used just this code, and they didn't want to change too much in that code. So they used it also for Brueckner calculation, just for the positive energy solution. So that's basically that. But from this here, you see you get only the sigma plus plus, because you have only the G plus 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 here. You don't know what is sigma minus. You don't know these parts of the masses. So there are many approximations in the literature now for those sigma minus plus or minus minus. I just gave you perturbation theory, projection of Lorentz invariance, Green's function techniques, and they all agree for symmetric nuclear matter, but they disagree for non-symmetric. And there are big fights for more than 20 years. And there is one, I should say, one full solution by Katayama in Japan, but this is they get very strange results, and we cannot reproduce it. We don't really know. The paper is also very short, so I don't know really right what they're doing. There is another solution by our chairman here, but this is used on a very different force. This is used on the spectator method on a different equation. I told you there's differences in the equations, and this goes also a little bit beyond. They take into account the randomization effects, they have randomization parameters, a complicated paper, but in principle they solve this, but it has nothing to do with our calculation. Okay, so what we are solving now, we solve also this part of this G matrix where you have plus minus, and this is a more complicated coupled system, but it can be done, and these are the results. So we have here the results. This is our work, this is red line. Then we have a work from Weigel's group in Munich. This is very close to ours. This is a Green's function technique, but it's not a full solution. And then it's this Japanese work. It's very different. We don't understand. And this is basically the result. That is if you do a proper job there, then you get more or less for symmetric matter. It's no different. The real big difference comes for asymmetric. Now you also have a momentum dependence of these different potentials, and they are usually rather weak. We agree on that. The density dependence looks like that. So it's all details. I don't have the time to go into that. And this is the final result. And then you get the results for nuclear matter, for instance, the compressibility. And these are many of these, some of them phenomenological, and then also non-relativistic compared here. Yeah, the difference here is really the isospin dependence. So if you do the full thing as we have done it here, you find that the scalar mass, that is m star, in the isospin dependence is different for neutrons and protons. And in the projection method, you get the same, but a different size of the splitting. And for the momentum independence approximation, you get just the opposite. So we have now clarified that this was more or less the right thing to do, but this was not clear so far. Okay, so we applied that for the symmetry energy. Here you see the final results. And we also used this calculation for the mass relation to calculate the mass relations for neutron stars. And you see this comes out here. So this is in the region where it's reasonable experimentally. Okay, so conclusion is relativistic Brueckner-Hartree-Fock is a successful microscopic tool. The full solution in nuclear matter was missing in the last 40 years. This gap has now been solved. Exact results are in agreement with earlier approximations. Now, how can we improve? Yeah, this is now our idea. We want to make a relativistic VLOK. So at the moment, my Chinese student solves these VLOK equations for the relativistic case. And if we have that, we can do Brueckner and finite nuclei in a much simpler way. And then we can use other relativistic nuclear forces. The problem is that there are not so many around. Most of the relativistic forces are this bond potential. And so the question then also, do we need relativistic three-body forces? At the moment, we have not included them, but we have still not the full agreement. The question is it also Brueckner is only an approximate theory? So do we need three whole lines or something? So these are all questions which are open. Now, in order to solve that, there's a collaboration with this Chinese group of Li Shengeng, and they introduced a chiral NLO force. And you see these are these phase shifts and these fitting holes. If you go in all the details, then you see, for instance, for this one S0, there they get more or less, the answer is they get more or less the same result as the experimental values, but in lower order. So if you go to N3 LO in the non-relativistic case, you need here only N2 LO. So again, the same thing. If you include relativistic, things get simpler. That's the old thing. nuclei, you don't do it, it's not necessary to do it relativistic. You can include higher order terms, but then the thing gets very complicated. So this is always the same here. Now, outlook for the future, I told you already, we are working on Brueckner theory with renormalized forces. If we have that, then we can check many things. How the local density approximation works really, nobody knows. We want to also get a tensor force for heavy nuclei, and then we can go to heavier nuclei with this finite calculation. We can investigate deformation, pairing, optical potential, and many other things. So these are some thanks to the collaborators who are working on them and some papers. And thank you very much for your attendance. Thank you. You can come here.
Now it's on. Now it's on. Oh, now it works. Okay. Then I may start. Peter, you mentioned our approach or our attempt to calculate the Dirac-Brueckner, including the Dirac-C actually. And that is always the problem.
In that end, we have massive.
And if you do so, you should start with a free space interaction, which does the same thing already in free space. Otherwise, you will fail. And there's only one interaction around as at that time, and still it's the same also at this time, which does that. And that is an interaction modeled by or derived by Gross and Machleit in the early 90s or mid 90s. And that is using the spectator approach, which you, without going into the details of a lot of things, which you mentioned. And so since they used this approach, we also had to use the same approach in the medium calculations. And what you find is that in the medium, this coupling to the Dirac-C produces a very strong momentum-dependent contribution, which brings you a very strong repulsion at high densities, which might be reasonable for certain effects like neutron stars maybe and those things. But there are no constraints on these particular effects of the density or this induced density dependence by the momentum dependence of the interaction. In particular, the vector channel plays a very important role in producing those effects, which is not a surprise because that is where the repulsion comes from.
Yeah.
And in order to get or go beyond that point, one needs first to do precise calculation within the same scheme in free space. And since we didn't see at that time when we did these calculations a chance to have that realistically done for free space, we did not continue with this project.
No, the problem is like in the Waleczka model. It was a big progress of Waleczka that he introduced the no-C approximation. Of course, the C plays a role, but if you go into this scheme, you have to do remnant and you end up nowhere. And this is much more complicated. So Waleczka is no Z approximation, and in that sense is similar. We just use the Thomson equation and nothing else. This is general in the community. Of course, you can do better, but then it's all open.
Then you open up it's a box of Pandora.
Exactly.
And, that's why.
And we also don't want to do that. We want to get a microscopic interpretation for the relative successful relativistic density functionals, and therefore we start from this Thomson equation and the interaction which is fitted there.
Yeah, that's what I did with Christian Fuchs, and then later with de Jong, that we took the usual equations as you have presented it. That means only the positive energy states.
Also this new work of this Peking group for this new relativistic NL3, they also use the Thomson equation. That's
maybe one final remark on the three-body interaction. So our experience is you need to introduce a relativistic three-body interaction on the level of 1% or something like that, and then you are really perfect on the saturation property.
No, this we are completely open. We have not fully got the good results. So if this is just Brueckner, we have to go beyond the two-hole line approximation, or do we need three-body forces? That's all, relativistic three-body forces. This is still an open question.
Thank you very much. I was wondering how to deal with the relativistic chiral interactions. That was the last part of your talk, right?
Yeah.
So you have the relativistic effective field theory, so to say. Yeah. I think there is a problem with this kind of theory, and the problem is that you want to separate short range from the long range effects, right?
Yeah. So
in momentum space, you want to get rid of high momenta, which means that you separate short range from long range. Yeah. But in the relativistic theory, this is different in principle, because you can be a very short range in the Minkowski space, like you can have very small interval. Yeah. But in fact, if you're close to the light cone, this spatial part of this interval can be really big. So you don't have a clear definition of the separation if you're in four-dimensional space.
But I mean, in non-relativistic chiral series is also not a clear definition. There's just a fit parameter there.
No, I'm talking about when you can be really far apart in the three-dimensional space and be have very small distance. So short distance in 3D and short distance in 4D are two different things.
Yeah, that's true. But
so this is not really well. I've heard
this is always a short distance problem in all the series.
Yes, this is well known in high energy.
The idea of this chiral series is to just fix this, and that's the same done here.
Yes, but can you check if you remain covariant, for example?
No, for sure not in that. This is always none of our series is completely covariant. The important thing is one needs these large scalar and vector fields. That's the problem.
Okay, maybe we can further discuss it then.
Okay, there was one more. No.
So, if I understood correctly, there were certain observables starting from Ab-initio theory, where people said now that we might need three-body forces.
Yeah.
If I understood one of your remarks correctly, that might not be true if you have a fully relativistic theory, and two-body forces might be fully sufficient.
This was basically discovered in 1980 by Anastasio and these people. They did relativistic Brueckner in nuclear matter, and they found they get saturation without three-body forces.
So
this was
what people claim nowadays, that they want to study three-body forces in light nuclei to test the predictions of ab-initio theories. That might just be the ab-initio theories missing some relativistic aspects of the theory.
Exactly, you are right. That's what we are hoping. We want to do ab-initio and without three-body forces, because for us, the three-body forces are not really ab-initio, they are fit parameters.
Yeah, of course.
They certainly need to include the three-body forces, but they model these three body forces in terms of other diagrams. And all these diagrams, at least at the NL3, they are resummed completely already in the relativistic approach. And so this is a more efficient, optimized approach in that sense. And that is an unsolved controversy, I think, between the relativistic community and the ab-initio community. And they have a different view on this, and you may certainly always resolve this resummation into the different terms, and but then you are in danger to have to sum over many single contributions instead of expressing things in a simple manner.
Yeah, I think there is also there is the very well-known problem that's called Thomson collapse, and this is the phenomenon which occurs in if you have two body forces only of zero range kind. You don't even have a ground state. It's not converging, and this only occurs in non-relativistic theory. So if you do the same thing relativistically, you don't have this, and that's why people are talking about effective relativistic three-body forces, which are basically originating from the two-body. They have two-body origin. So that's another thing which is, I think, very rarely discussed in that community. I mean, I heard people talking about regularization or renormalization of this problem, like this zero range forces, but I'm not sure if this is equivalent to the adding three body forces on the same level. So
okay, we have one question from Zoom. So maybe if Sagava-san, you can ask your question.
Yes, I have one comment and one question. One comment is this compressibility problem of superfluidity and non-superfluid nuclei, this lead-208 and tin isotope and cadmium isotope. And we studied systematically both closed-shell nuclei and superfluid nuclei with Hartree-Fock and RPA and Hartree-Fock plus, HFB plus QRPA. And our conclusion is we can consistently understand both giant monopole resonance with EDF with some incompressibility 225 plus minus 20. That is somewhat smaller than which Peter you show in your slide. You show 240 plus minus 20, but this number should be slightly going down by our self-consistent RPA calculation. And also, Bawan Lee did the Bayesian analysis of these all data set, and his conclusion is exactly same as our conclusion. Compressibility 225, then we can systematically understand giant monopole state. So that's one comment. And this another question is, okay, this relativistic effect may induce automatically kind of three-body host, NN bar type three-body host. But how about Miyazawa Fujita type three-body host, this delta excitation? That's also kind of a big contribution to the three-body host. So I think that is some extra effect than the relativistic effect.
Yeah, certainly there are three-body forces there, but I refer again to this Catania paper of Lombardo and collaborators that they included all these different excitations and also these set diagrams of the relativistic part. And they found, at least for saturation densities, not for higher densities, but up to saturation densities, the most important part is this relativistic term. So the others are partly canceling or not so important.
Yeah, because this Miyazawa-Fujita type is kind of short range type. I mean,
you must.
So that high momentum transfer. I mean, the phenomena.
Certainly. I mean, I don't understand the details of these calculations of the Gasania group, but their conclusion is basically the most important part comes from the set diagram. At least the saturation density. If you go to higher density,
higher density, maybe the story is slightly different, I think.
Okay, I think we have to stop now and move to another talk. Let's thank Peter once again.